Water falls without splashing at a rate of 0.25 liters per second from a height of 2.6 meters into a 0.75 kilogram bucket on a scale. If the bucket is originally empty, what does the scale read 3 seconds after water starts to accumulate in it? So I drew a pitcher with water, and the pitcher is tilted slightly. So this is the pitcher. It's tilted slightly to the side so that water is pouring into the bucket. The pitcher has nothing to do with the problem. It just makes sense for me for the water to be pouring from somewhere. The starting height is 2.6 meters of the water, and it's right above the bucket, relative to the bucket. And the velocity of the water is 0.25 liters per second. And liters is a weird unit. We're going to get to the bottom of that later. And I divided time into two components. Time one being the time that it takes for the water to fall 2.6 meters into the bucket, because in the question it says 3 seconds after the water starts to accumulate. So that's time one. And then time two being 3 seconds, which is stated in the question. And then small m being 0.75 kilograms, representing the mass of the bucket. So this is the direction of everything. Okay, I made down positive just to make things simpler, and I used two kinematics. You could have used one, but I wasn't really thinking. So you could have just used change of y equals velocity naught times t plus 1/2 at squared, but I did not do that. So I'll show you what I did. Change in y is equal to 2.6 meters, given. Velocity naught is equal to 0 meters per second. Not given, but just intuition kind of a thing. And then acceleration is equal to 9.8 meters per second squared. That is given, or not given, but also intuition kind of thing. Okay, anyways. And then time one and velocity final, we do not know. So we could have just done the first kinematic, which I just mentioned. But what I did is I split it into two kinematics because I can't algebra and a quadratic is too much for my brain. So I just split this into velocity final, and then I got velocity final. Sorry, I didn't split this into velocity final. I used this kinematic, which excludes t, time, then found velocity final, which is approximately 7.14 meters. And then 7.14 meters, I plugged into another kinematic, and then now I just isolate t, time. And then you get time one is equal to 0.73 seconds, approximately. So then here we have change in volume is equal to velocity times time one plus time two. So that makes sense because of what I explained earlier with time one and time two. So 3 seconds after the water starts to accumulate. And the water starts to accumulate after 0.73 seconds. So we use the speed, 0.25 liters per second, times the time to get the change in volume, 0.93 liters. So what can we do with liters? Well, for starters, we can convert this. Please leave me alone. Okay, we can start, that just ruined my train of thought. We can convert this to meters cubed. Why is that important? Well, first, this is the answer, 9.3 times 10 to the negative 4 meters cubed. We can use the density of water. So that's not given in the problem again, but you kind of need it in order to solve it. So 1 gram per centimeter cubed is the density of water, rho H2O. And if we just convert this to kilograms per meter cubed, we get 1,000 kilograms per meter cubed. And the goal of this is to multiply this value by the density in order to get the mass of water. Rho equals mass divided by volume. Makes sense, basic definition of density. And then plug and chug, we get mass is approximately 0.93 kilograms, or 9.3 times 10 to the negative 1 kilograms. So now we just sum up our forces, and that's going to give us big M, the mass of the water, plus small m, the mass of the bucket, times acceleration, which is just the gravitational constant, g, lowercase g. And then we just add these masses up and multiply by g, and we get a weight of approximately 16.5 newtons.